Hey there, take a look around you for a second. Seriously, the air you're breathing, maybe the coffee on your desk, just about everything is a mixture. So today, we're going to dive into the chemistry that explains how all these things come together, or, sometimes fall apart.
I mean, have you ever really stopped to think about it? Why does sugar just, poof, disappear into your tea? But if you try the same thing with sand, it just sinks right to the bottom? It seems like such a simple question, right? But the answer is actually pretty deep, and it all boils down to the science of mixtures.
Let's just take your morning routine. That cup of coffee you've got? Yep, that's a classic mixture. You've got water, all those tasty coffee compounds, maybe a little sugar in there. And how about the air you're breathing right this second? It's not just one thing. It's a whole mix of gases like nitrogen and oxygen. Heck, even inside our own bodies, our blood is this incredibly complex mixture of cells, platelets, and plasma all moving around together. Or think about that can of paint you might have in the garage. You know you have to give it a really good stir before you can use it. So see, coffee, air, blood, paint, they are all mixtures, but they act in totally different ways. All right, so here's how we're going to break this all down. First up, we'll cover the two main types. Then we'll get into the perfect mix, solutions. After that, the chunky mix, suspensions. And we'll finish up with the weird in-between category, colloids, before we see how your whole world is remixed. Okay, let's get into it. All those things we just mentioned, the coffee, the paint, they can all be sorted into two big groups. And honestly, getting this one big divide is the key to understanding why they all act so differently. But first, what is a mixture, really? Well, the most important thing to remember is that it's a physical mix, not a chemical one. The different parts are just hanging out together. They haven't chemically bonded to become something brand new, which means, theoretically, you could always separate them back into their original parts. And here it is, that big divide I was talking about. You've got homogeneous and heterogeneous mixtures. So homo means same. A homogeneous mixture looks exactly the same everywhere you look. Think of lemonade. Hetero means different. With a heterogeneous mixture, you can actually see the different bits and pieces, like our sand and water example. It really just comes down to whether it's uniform or not. All right, let's tackle our first category, solutions. This is what we're talking about when it seems like one thing just completely disappears into another. It's the perfect mix.
Okay, so here's the nitty-gritty. A solution is a homogeneous mixture where the particles of the thing being dissolved are insanely small. We're talking less than 1 nanometer. To give you some scale, a single human hair is like 80,000 nanometers wide. So these particles are microscopic. They're so tiny and so well mixed that they'll never ever settle out. Once it's mixed, it is mixed for good.
Now, to really get a handle on solutions, you gotta know the lingo. There are two key players here. You have the solute, that's the stuff that gets dissolved, like sugar, and then you have the solvent, that's the stuff that does the dissolving, like water. The solute gets dissolved by the solvent. Pretty straightforward, right? So that leads to a good question, right? Can you just keep adding sugar to your water forever? Is there a limit? Is there a point where the water just kind of says, nope, I can't take any more? And the answer is a big yes. There's absolutely a limit. When that solvent can't possibly dissolve any more solute, we say the solution is saturated. A super cool and delicious example of this is making rock candy. You basically make a supersaturated solution. That means it's holding more sugar than it should, and as it cools down, all that extra sugar has nowhere to go, so it crystallizes out. Okay, so that's what happens when everything mixes together perfectly. But what about the total opposite? What happens when things just don't mix? Well, now we're getting into the world of suspensions. You know, those mixtures you always have to shake.
And guess what? It all comes back to particle size again. In a suspension, the particles are massive compared to a solution. We're talking more than 1,000 times bigger. They're just too big and too heavy for the solvent to keep them floating. So eventually gravity wins, and they settle right down to the bottom or float to the top.
You can see this for yourself so easily. Just try the sand and water test. Go ahead and stir it like crazy. It doesn't matter. The sand and water will never truly mix. The sand is just insoluble, and if you wait just a minute, you'll see it all sitting at the bottom of the glass again. That right there is a suspension. And this is exactly why you see that little instruction, shake well before use, on so many
things. Think about certain medicines or even a vinaigrette salad dressing. The reason you have to shake them is because they are suspensions. All the important bits have settled out, and you've got to shake them up to get everything mixed back together before you use it. Okay, so we've got the perfect mix with solutions and the total non-mix with suspensions. But what about everything in between? What about that murky middle ground? Well, now we get to the really fascinating stuff, colloids. These guys are the masters of disguise. Colloids are basically the tricksters of the chemistry world. Why? Because to the naked eye, they can look perfectly mixed, just like a solution. But secretly, their particles are way bigger. They're not quite big enough to settle out like in a suspension, but they are big enough to do something really, really cool with light. And this is how we catch them. There's a test called the Tyndall effect. It's awesome. If you shine a beam of light, like from a laser pointer, through a true solution, the light just goes straight through. You can't really see the beam inside the liquid. But if you do the same thing with a colloid, bam, those bigger particles scatter the light and you can see the entire beam passing through the mixture. It's the dead giveaway that you're looking at a colloid. And you will probably be shocked to learn just how common colloids are. I mean, they're everywhere. Milk, mayonnaise, butter, those are all a type of colloid called an emulsion. Things like gelatin and jellies, those are gels. Whipped cream and soap suds, foams. And even things like fog and bug spray, those are aerosols. All of them are colloids that we use every single day.
All right, so we've gone through the big 3 types of mixtures. Let's pull it all together and do a quick recap. It's pretty cool to see how this stuff gives you a whole new way of looking at the world.
This little chart here really is the money shot. It lays everything out side by side. What you should really take away from this is that solutions, colloids, and suspensions aren't 3 totally different things. They're actually all on a spectrum. And the one thing that determines where they fall on that spectrum is particle size. From the teeny tiny particles in solutions to the huge ones in suspensions and those tricky mid-sized ones in colloids, it all comes down to size. Size is everything here. So I want to leave you with a final thought to chew on. If you think about our world as one giant mixture, with the oceans, the air, even our societies, which one do you think it is? Is it a perfectly blended solution, a clearly separated suspension, or is it something more like a complex, kind of cloudy and fascinating colloid?